Students, we're continuing with the PowerPoint from chapter 7 that has to do with Planck and Einstein and photons and the photoelectric effect. And I ended the last one, which I called part 1 of this. So this would be part 2 of this PowerPoint narration. And I ended it, if you're following along in the packet, I'm doing this problem on page 59. I do these problems on page 59. So in front of you right now, you should see that PowerPoint slide. So there's 2 problems on this slide, and we'll do one and then the other. So the first one says the total light energy released by a source is 57 kilojoules over a 2-hour period. And then the wavelength released of light is 351 nanometers. How many photons are released in the 2 hours? Okay, so I'm going to switch over so you can see me do this problem on live. Okay, so you should be able to see that now. And so in this problem, we're given that there are 57 kilojoules that are released over a 2-hour period. We're also given that the wavelength of the light is 351 nanometers. And we want to know how many photons are released in that 2 hours. So we're looking for number of photons in 2 hours. So that summarizes the problem. So we're looking for number of photons. So 57 kilojoules is an energy, and that's not the energy of one photon. The energy of one photon is always a really tiny, tiny number. So, and this is a light source. So this is all from a light source. Doesn't tell us what type of light source, but 351 nanometers is ultraviolet, so it must be some sort of ultraviolet light. And so this 57 kilojoules is energy, because kilojoules is energy. So that must be that's the total energy that's being released. So if you imagine we have this light source, so here's some sort of light source here, and it's releasing photons. Okay, so all those little dots and dashes are photons. And it's on for 2 hours. And so what we're asking is, in that 2 hours, so this is continuous over 2 hours, how many photons are going to be released? So if we could count up those little dots, so to speak, of photons, how much would be released in 2 hours? And the photons correspond to light of wavelength 351 nanometers. So what we know is that over that 2-hour period, the energy released, the total energy released is 57 kilojoules. So that's the energy of the photons released, their total energy. So we want to know how many photons that is. So we're going to use this equation that I mentioned in the last problem we did. Energy total is equal to the energy of a photon times the number of photons, which, like I said, isn't really an equation of science, so to speak. It's just common sense. If you have energy coming from a source and the source's energy is due to a lot of little particles, then if you know the energy of each particle here, and you multiply by how many of them there are, you'll have the energy total. I sometimes use the analogy, it's like, let's say you have a bag of M&Ms. And let's say I told you that each M&M was 5 calories. Well, that's the calories of each one. So if each one's 5 calories and you eat 10 of them, then you've consumed a total energy source of 50 calories. So it's the same idea, only instead of M&Ms, we got photons. So in this case, in the last problem, the one that we did in the packet, that's printed in the packet right before this, we knew it was sort of the opposite problem. In that problem, we were looking for the energy total. We were given the number of photons because it said 1 mole of photons. And we could calculate the energy of the photon because we were given its frequency. So then we were looking for energy total. But remember, I told you before in this course, whenever you're given an equation or you know an equation, we might do it one way in class, but think about, well, how would I solve for a different variable? These are just 3 different possible questions I could ask. So in this question, we are asking this: what is the number of photons? Because that's what it says in 2 hours. So what that means is if we take our energy total and divide by the energy of each photon, that'll tell us how many photons that we have. So the energy total is given to us because they told us that it's 57 kilojoules. Now, the weird part about this problem is this 2 hours we don't have to think about, because the energy total is in 2 hours and they're asking the number of photons in 2 hours, so it like cancels out. If they gave us the energy total in 2 hours, but they asked for the number of photons in 1 hour, we'd have to worry about the time. If they gave us the energy total in 1 hour and they asked for the number of photons in 2 hours, we'd have to worry about taking that into account. But because these are the same, the energy total is in 2 hours and the photons are in 2 hours, we don't even have to think about it. Okay, so the energy total we said already is 57 kilojoules. So that we already have. So we already have this, check. So therefore we just need to find out the energy of a photon of this light. Well, they told us that the wavelength though is 351 nanometers. So let's see there. So we can get the energy from that. And there's 2 ways to do that. So I'm going to scooch this up here now, okay? So we know that the energy of a photon is equal to h, which is Planck's constant, times the frequency. So if we have the frequency, we can just go straight to there. We also know that speed of light is equal to the wavelength times the frequency. Those are 2 equations that you're supposed to know, okay? We can combine those 2, and I showed you that in a different example, I think. And that is that we can solve this equation for frequency. So if I take c divided by wavelength, I'll get frequency. And then we can substitute this part into here. So there we'll get energy of the photon is equal to h, and then a frequency, I'll have c over lambda. Sorry. So all I did there was substituted that frequency with c over lambda from this equation, and energy of a photon is hc over lambda. So that's a nice one. You don't have to memorize it because it actually you can derive it, but it's nice to have if you do know it. Okay. So then what we can do now is calculate the energy of our photon in this problem. The energy of our photon is going to be hc over our wavelength, and our wavelength was 351 nanometers. Now, when I put the numbers in for h and c, what's going to happen is that the c is going to have units of meters per second. Okay, so h is going to be 6.626 times 10 to the minus 34 joules times seconds. You don't have to memorize these, they would be given to you. C is equal to 3.00 times 10 to the 8th meters per second. And so when I multiply those 2 together, when I take h times c, what's going to happen here is those seconds will cancel out. And so on the top, once those seconds cancel out, I'll be left with the units of joules times meters on the top. Because see, this seconds will cancel out that one, okay? And so I need my wavelength here to be input into meters so I can cancel this out here, okay? So it was 351 nanometers. I could do a little side calculation, but you don't have to do that. It's a little bit easier to do it this way. 351 nano is 10 to the minus 9. So I can just say times 10 to the minus 9 meters. So that 10 to the minus 9 is nano. Now this is not proper scientific notation, but who cares? Because we're gonna just input it into our calculator. So I'm not gonna rewrite the h and the c. You got h and you got c there. So we multiply those together. I would divide by 351, 10 to the minus 9. The meters now will cancel out, and I'll get that energy of the photon, and you should do this on your calculator to prove it to yourself. The energy of this photon comes out to be 5.66 times 10 to the minus 9 joules. Okay. Why don't you pause for a second and make sure that you get that. Use your calculator, take HC, make sure you got that, come up with that 5.66 times 10 to the minus 9 joules. So pause the video and then come up with that answer. We're not done yet, but that's step one. Okay. So I assume you're back from pausing the video. I'm going to take another piece of paper here. One sec. You're right there. Okay, so what we had up here is we said before that what we needed was energy total divided by energy of a photon is equal to the number of photons. That's what we're looking for. So this is the equation that we're trying to use. And we just found out the energy of a photon. But we said we had energy total because they told us that it was 57 kilojoules. So we know from before that energy total is 57 kilojoules. That's what they told us in the problem. There's a little issue here in that we have a kilojoule here and just a joule here. So we're going to have to take care of that. So I'm going to go up to that top equation. I'll recopy it here for a second. Energy total divided by energy of a photon is equal to the number of photons. My energy total is that 57 kilojoules. So I'm going to write 57, instead of writing the K, I'm going to write times 10 to the third joules. So this is my kilo, because remember we learned that, we memorized that that's what kilo is, 10 to the third. And I'm going to divide that by my energy of the photon up here, 5.66 times 10 to the minus 19 joules. And it cancels out because now we're just looking at a number. The number of photons is what this is going to come out to be. If I divide those two numbers, I'll get the number of photons. Only 2 sig figs allowed because of that. 57 only has 2 sig figs. And I get 1.0 times 10 to the 23rd. And that's my number of photons. So what does that tell us? Well, that tells us that when this light is shining for those 2 hours, that it will release during that 2 hours 1.0 times 10 to the 23rd photons. That's how many, if we could count them, that's how many would come out. Okay, so we're going to do another one. I'm going to flip back for a second to the PowerPoint so we can see the problem. Give me 1 second here. So I'm flipping back to the PowerPoint slide now. Hopefully this works as it gets stuck. Okay, so here we go. So number 2 says a watt, and you've probably heard of watts before. If you have in your house an electrical appliance or on a light bulb, it tells you the watts. So now it's telling us what a watt is. A watt is a unit of something called power. And power is the energy that is taken in or released by something over time. So for example, 1 watt right there is 1 joule per second. So something that is either consuming 1 watt or releasing 1 watt of power is releasing 1 joule every second or taking in 1 joule every second. So now we're not just looking at the energy that is there, but we're seeing it as a function of time. So if you have a 60 watt light source, so if it's labeled 60 watts, and in this case, it's emitting only 1 wavelength of light. So it's not a white light like a light bulb in your lamp in your room. It's only red light because it's 622 nanometers. That's red. So how long will it take for it to emit 100 moles of photons? All right. So it's another one of these energy total, energy is equal to energy photons times number of photons problem. It's just that now we have this time thing thrown in there. So there's a little extra difficulty here. I do want to say that this problem is not really realistic for a real light source. And that's because if you have a real light source that is labeled 60 watts, it's taking in 60 joules per second. That's what 60 watts would be, 60 joules per second. But that's how much energy it's taking. So if you have it plugged into your outlet, it's consuming 60 joules of energy every second. That doesn't mean it's putting out 60 joules of light energy per second, because you probably realize if you go to touch a light bulb, it gets hot. So the energy it's consuming, only part of it's going to light, and a lot of it's going to heat. Depending on the light source, depending on what type of light it is, could be as little as only 10% is getting to light and the rest is going to heat. So this is not the most realistic problem, because we're saying that, we're assuming that it's all just becoming light. But, we'll show you how to do the calculations. I've seen ones where they say things like, assume only 10% of the light, of the energy goes to light. So then you'd have to factor that in too. So we'll just keep it simple on this one, or relatively simple. So I'm going to flip back over to my camera here so we can do the problem. So here I go. All right, so you should be seeing the camera again. So, so now we're going to go to this problem, and I think I'll take a fresh piece of paper. Okay, so in this problem, again, we're going to say that, so let's talk about what we have. We know that we have a power on this, and the power is the 60 watts, okay? And they told us that watts is just an abbreviation for joules per second. Okay, so that's 60 joules per second that we are, that this light source is putting out. So, sorry, one sec, my paper out here. So, and it's telling us that the wavelength that this is emitting or releasing is 622 nanometers. And the question is, how long will it take? So we're looking for time. How much time will it take to release 100 moles of photons? So 1 mole is Avogadro's number, so we have 100 of those. And so this is also going to be an energy total is equal to energy of a photon times the number of photons problem. Only now we have the number of photons. This is our number of photons, 100 moles. That's our number of photons. The energy of the photon we're going to get in the way we just got in the last problem, because we have the wavelength. So that's going to help us calculate that. And so we'll be able to get the energy total of that 100 moles of photons. How are we going to get to time? Well, we're going to use this, because this tells us energy per second. So if we can get the total energy that comes out in that 100 moles of photons, and then we can use this that tells us how much energy is released per second, we can get to time. So let's figure out the energy total of that 100 moles of photons first. So we need that energy of a photon. We have to calculate this. So energy of a photon, we're going to use what we used the last time, because we have the wavelength, so it's easier to say hc over the wavelength. I'll write it out this time. H is 6.626 times 10 to the minus 34. Units are joules times seconds. C is our speed of light. Which is 3 times 10 to the 8th meters per second. Lambda is our wavelength. So I'm going to do what we did in the last problem. Instead of converting to meters in a separate problem, I'm just going to say, well, I know that nano, that little n, is 10 to the minus 9. Makes things faster that way. And when you're doing a test or a quiz, you don't, even though you're doing it online, you want to have enough time to do your problem. So take advantage of the shortcuts. So if we look at our units, the meters cancel, the seconds cancel, and we're left with just joules, which is what we want, because we have energy of a photon. And so pause the video and put those numbers in your calculator and see if you come up with the same answer I do. I'm having you do this because sometimes people, even at this point in Chem 200, get a little bit messed up with scientific notation in their calculator, especially when they're dividing. So if you don't get the same answer I do, then kind of put it aside and maybe shoot me an email, and we can have a little meeting and I can show you what you're doing wrong on your calculator, okay? You can hold it up to the screen for me or something, or tell me what buttons you're pressing. So, but a lot of people will probably get it right. So pause and do a little calculation. Okay, so I'm assuming you're back from that pause. And if you are, you should have gotten energy of the photon is equal to 3.20 times 10 to the minus 19 joules. You might see this a lot, 10 to the minus 19 joules for energy of a photon. For photons that are in the visible or almost the visible, like the UV close, like UV that's pretty close to the visible, or infrared that's pretty close to the visible, when your wavelength is in that 100 to 1,000 nanometer range in there, that's usually what you get for their energy. So that's a good hint that you're doing something okay. If you get some number at that point that's not 10 to the minus 19 and your wavelength is in that 100 nanometer-ish range, then you need to double check your math. Okay, so that's what you should have gotten for energy of the photon. So we're going to go back to that equation right there at the top. Energy total is energy of the photon times the number of photons, and we're going to calculate the total energy. So energy total equals energy of the photon, which we just have there, times the number of photons. But remember, we said we have 100 moles of photons. So 1 mole would be Avogadro's number worth of photons. We have 100 of those. So we're going to say 100 moles times that there are 6.02 times 10 to the 23rd photons in 1 mole. So there's 6.02 times 10 to the 23rd anything in a mole. If you're talking about molecules, it's molecules, atoms, electrons, whatever you got. We're counting photons, so that's how many photons are in a mole. Okay? So if I do multiply all that together, my energy total is 1.93 times 10 to the 7th joules. So that's the total energy. So let's review what that is. We have a light source. We know it's 60 watts. It is releasing light of wavelength 622 nanometers. And we're saying it's going to release 100 moles of photons, 100 particles of light, 100 moles particles of light, 100 times Avogadro's number of particles of light. And we want to know how long that's going to take. So we want to know time. So we know the total energy that's going to be released, but we also know that because this is the power and watt, we were told in the problem, you don't have to memorize what a watt is. If I needed you to calculate it with it, I would remind you, just like it is, I would write it just like it is in the problem. So it tells us that 1 watt is the same as a joule per second. So this is telling us that this light source is releasing 60 joules of energy every second. We know that the total energy released in that 100 moles of photons is this many joules. So to figure out the time, 1.93 times 10 to the 7th joules times, I want to cancel out joules and I want to get to seconds. And it tells us there's 60 joules released every second. Okay. Now, you can do that calculation and it would give it to you in seconds, and it comes out to be a really big number. So if you just did it on your calculator, I'm not even going to write it down. It's such a big number. So what I did is I said, okay, it's a really big number. So let's go, you can go from seconds to minutes and then minutes to hours, or you can go directly from seconds to hours if you realize that 1 hour is 3,600 seconds. That's 60 times 60. Okay. Or you could do it in 2 steps, minutes and then to hours. If I do that, the joules cancel, the seconds cancel, and I get hours. So 1.93 times 10 to the 7th divided by 60 and then divided by 3,600 will give me 89 hours is how long that would take for that to happen. 2 sig figs, because that was given to us as 2 sig figs in the problem. If I go whoop, way to the top here, it told us 60 watts. It had a decimal point in there, and that means that 0 is significant. So 2 sig figs. Our 100 moles had 3 sig figs. This number had 3 sig figs, but this is going to limit our sig figs in our answer to 2. So back down to here, and then our answer is 89 hours. So that's our time. So that means it's going to take 89 hours for this light source to release that 100 moles of photons. So that's the end of that problem. Those answers are in the packet, but I thought I'd work them out for you so you can see. So I'm going to end this video now, and then you can continue with the other topics. This is the end of this topic in the PowerPoint. I'm sorry, in the packet. The next topic is going to be continued. So we just finished up in the middle of page 59 of the packet, if you're following along with the packet. Oh, wait, you know what? That might be the wrong page number. Ignore that page number. Sorry. We're going on to a different topic now. Now we're going to talk about line spectra. Sorry about that error on the page number there. I'm looking at a different version of the packet, an older version. So just continue on with the packet from where we were, and then with the next topic. All right, bye.